In topic 4.3, the standard model, we're going to be looking at the standard model, sometimes referred to as the standard model of particle physics or the standard model of elementary particles. You can see there that we're going to get on to looking at defining the concept of an elementary particle and an antiparticle, but before we do, we're going to have a look at what the standard model is just from a broad brush perspective. And you can think of it as being a classification system. So trying to break down what particles are into subcategories, and it's a classification system for elementary particles. Now that term elementary particles is one that we need to have a good definition of, and so the definition from the syllabus in the glossary is that it's a particle whose substructure is unknown. And I don't think that's a nice clear definition. Another way to think of it, it's a particle that we think can't be broken down into anything smaller. Now, while we're dealing with elementary particles here, keep in mind that our understanding of elementary particles has developed over the years, beginning from the discovery of the electron really in 1897. Before that, atoms were thought of as being elementary particles, that they couldn't be broken down into anything smaller. The discovery of the electron showed that electrons came from the atom, and then we had that progression of development through Rutherford's model, through the Bohr model, and so on and so forth, where smaller and smaller particles were being discovered. So protons and neutrons likewise were thought to be elementary at one point, but we'll see as we go through the standard model of particle physics that they too can be broken down into smaller parts. The easiest way to identify what the standard model is in a table, and the one that we're going to refer to looks like this. If you Googled it, you'll find a number of different representations, but they all have the same structure to them. Now, before we get into what each of these particles are and what the subgroups are, there's a couple of things to mention here. This model was developed through a lot of experimentation, but also through theory. So a lot of these particles were first theorized to exist before they were actually discovered experimentally. As we said, the electron, it was discovered back in 1897. It wasn't until 1937 that the muon was discovered. The electron neutrino was discovered in 1956. The tau was discovered in 1975. The top quark, 1995, and you may recall back in 2012 the Higgs boson was discovered as well. We've already discussed the idea of the photon as well back in the early 1900s when Einstein was able to explain that concept in a bit more detail. But ultimately this model has been developed over a number of years, so sort of 100 plus years, and it continues to be refined. Keep in mind it is a model, so it does explain some observations that we can see about particles and about matter, but there are still some flaws. We don't need to worry about that in this course, but just be aware that there are flaws in any model, and the standard model still has some aspects about it that could be fixed, or with further discovery the model might be refined even further. You can see on the table that it's been subdivided into a few different categories. So the first one we're going to look at is the difference between fermions and bosons. So you can see on the left here we have the fermions. Now the idea of a fermion, the definition of what makes a fermion, is that it has a half integer spin. That's not something that you need to worry about in lots of detail. I'm just giving you the background so you understand the difference between them. So these particles have half integer spin. So there are other particles that have different spins associated with them. So the fermions are ones that have half integer spin. There are some fermions that are not elementary particles. So while it's true to say that all of these particles are fermions, it's not true to say that all fermions are elementary particles. So something to keep in mind. You can see there too that the fermions are broken down into two smaller categories. So this group at the top are known as quarks. And we'll deal with quarks in a bit more detail in a coming video, and this group down the bottom are known as leptons, and again we'll cover those in much more detail in a subsequent video. On the right hand side we have the bosons, and bosons are a bit of an unusual one. They are considered to be exchange particles, and what we mean by exchange particles is that they are involved with the mediation of fundamental forces We'll have a look at what those fundamental forces are and how the exchange particles are involved in another video. You can also see there that the bosons are broken down into two smaller categories. So this group of 4 bosons are known as gauge bosons, sometimes also referred to as vector bosons, in that they mediate the fundamental forces, or at least 3 of the 4 fundamental forces. And then the other type of bosons, or the one being the Higgs boson, is a scalar boson. Whereas the gauge bosons mediate vector fields, a scalar boson mediates a scalar field, so a field that doesn't actually have direction, it only has a magnitude associated with it, which is what mass is. It's a scalar quantity, so the Higgs field mediates that idea of mass, hence it's a scalar boson. Now, while we've got 17 particles in the standard model, there are actually a few more that we need to be aware of, so we'll just make a bit of a note about that. So the 17 particles are very much the fundamental building blocks of everything that we can see around us, but there are some other aspects to consider about matter, and the reason why we need to worry about more than 17 particles. Each particle also has an antiparticle associated with it, and an antiparticle is something that you need to be able to define. And the idea of an antiparticle is that it is a particle that has the same mass but opposite charge. And in some cases where we have particles that are neutral, it might be that it has an opposite spin as well. Again, that concept of spin is not one that we have to cover, but it's one that's important to identify as being a property that you can relate to, at least, that there is a property of spin to consider. So that's the idea of an antiparticle. To provide a little bit more scope, or a bit more of an example, let's have a look at the electron. So we've dealt with the electron in a fair bit of detail. We know that a few properties about an electron. So the antiparticle to an electron has the same mass as the electron, but it has the opposite charge. And that particle is known as the positron. And as we said, it has the same mass as an electron, but opposite charge, so that means it's positively charged. So it's not a proton, it's much smaller mass than a proton, but it has the opposite charge to an electron with the same mass as an electron. Another point to note about antiparticles is that if a particle encounters its antiparticle, and when we say encounters, we're really saying that it's sort of colliding with or interacting with. So if it interacts with or encounters its antiparticle, they will annihilate each other. So what we mean by annihilate is that all of their mass is converted to energy, so that they basically destroy each other, and they will produce 2 gamma ray photons. Now, if you look around you, all of the matter that you can see is matter. It's not antimatter. So there's very little antimatter in our universe. There are some situations where antiparticles are produced in particle interactions, but what will usually happen is that those antiparticles will very quickly encounter their corresponding particle, annihilate each other to produce gamma ray photons. So there's the basics of the standard model elementary particles and antiparticles. We'll start to break that down and look at some of those subcategories of quarks, leptons and bosons in the next few videos.